So welcome everyone to the 26th Journal Club session, the Student Journal Club session, which is jointly organized by Biopractify, Bioanalytics Skill Development Forum, ACS IIT Delhi, IIT Bombay, and various other student chapters. So welcome to the 26th Student Journal Club session, where our speaker for today, Mr. Nirmal Mallick, would be taking your a session on application of ANSYS CFD in bioreactor optimization. So, welcome Nirmal to this 26th Journal Club session, and thanks for taking out time for teaching students about the application of ANSYS CFD in bioreactors. And uh, I hope you will enjoy the session. So, are you able? Nirmal? Yeah.
Yes, I can hear you. Thank you, Vinit.
So let me give a brief introduction about you. Students, Nirmal Mallick is a PMRF PhD research scholar at IIT Delhi, and he is currently working under the guidance of Professor Anurag S. Rathod. And currently, his work is oriented towards the area of bioreactor design and optimization using advanced computational tools like ANSYS CFD and AIML, and he has completed his graduation from NIT Rourkela and his master's from IIT Guwahati. And he also had some work experience. He worked at CSIR IMMT Bhubaneswar as a JRF before joining his PhD. And I hope everyone would enjoy the session. And yeah, Nirmal, over to you.
Thank you, Vinit. Am I audible?
Yes, you are audible.
Okay. Should I share my screen presentation?
Yes.
Okay. Thank you. Okay. So, hi everyone. As Vinit has already given a good introduction about me. Thank you for having me here, Vinit. So, so as I have already mentioned, the topic the topic is about application of ANSYS CFD in bioreactor design and optimization. Okay, so uh, I'll give you a brief about how you can design using how you can use ANSYS and how you can use this tool for your future research if you like to. So, so if you at present, if you go for a Google Scholar search or Science Direct search, you will find at least like in Google Scholar, you will find 2 to 3 lakhs of journals regarding bioreactor design and optimization. Because this tool is not just it's not a new tool that is like recently launched. It is like it has been from 2008. People has been using this tool, ANSYS. And I remember that time when you were in graduation, there people used to have this Gambit version of it. We used to have a 2D version of the design. So it's a very old software. People has been done a lot of research on this, but the reason why I am showing these numbers to you is because it is still worth to jump into this area of research, or you'll just be like searching for novelty. So here I'll try to answer that question. So where you can find some directions. I hope if somebody looking for some direction how we can apply SA safety, or if in future if you want to do pursue in this direction or not. So when we talk about CFD, it's basically means hydrodynamic studies, right? So computational fluid dynamics. Okay. So if you have any doubt, let me. Sorry, you can ask me anytime. Okay. So if you have hydrodynamic study. So in hydrodynamic study, what we basically do is we'll calculate obviously the overall mass transfer coefficient, that is KLA, the bubble distribution, the effect of various physical parameters like height to diameter ratio or impeller diameter to the reactor diameter ratio, right? So this has been studied long before. It's not something new that we will be doing, but the temperature distribution, the pressure distribution effects, and the effect of different type of impeller, that is a area where you can surely use at present, where people are already doing also what this doing some research in that direction. So the pressure distribution, how it affects is if you increase the height of the column, the hydrostatic pressure at the bottom definitely increases. So that increases that varies the mass transfer coefficient. So in a long industrial level scale, when you are operating a 1,000 liter reactor or a 5,000 liter reactor, where this kind of hydrostatic pressure really affects a lot to it can minimize the side effects and get a good product out of it. That can be a good research topic in it itself. So next is apart from simply the hydrodynamic study, you can do some advanced studies like integrating cell growth mechanism to the cell and optimize your process itself, right? Or integrating machine learning algorithms to find a optimized region or optimized region to work in, like agitation rate, erection rate, what region you should be working in. Okay, so these are the areas still not completely explored. So where ANSYS CFD machine learning is can be implemented. So how the steps, what is the basic steps that you should be doing when you are doing an ANSYS safety modeling? What are the basic steps? Obviously, that starts with geometry design, and that is the most important step of the entire process. If you don't know how to properly design a geometry, which area, how to identify properly your geometry, then you cannot be like have a have a good solution, or your solution will never converge, right? So that is the most important parameter, like having a design, good geometry. Okay, so next step is grid independent study. What is grid independent study is basically grids are when you have a 3D geometry, you break that 3D geometry into millions of cells, small cells, and when you do the simulation, you try to optimize the kinetic energy or the loss of energies, the energy dissipations through in all the cells. So by grid independent study, you see how the when the effect of the size of the grid is basically reducing, or it has little to no effect on the on your result. Next, you have the case setup, and you will do the simulation. So, and when you have the experimental to the simulation error less than 10%, then you can say, okay, my design is now ready for the next step. So then you can have some, suppose you are designing some impeller, like you have an idea of having a new type of impeller that can give the same amount of KLA at lower RPM as compared to the Ruston turbine having 6 blade, which gives you around 900 RPM. In that case, you should first start with your Ruston turbine. You have to go through all these points. You have to go through all these points to come to this point that your reactor, now your model is ready for the new geometry to get into. So now once you have come to this much design validation, then you can implement your model. You can implement the new impeller geometry and see how that is affecting your KLA. Once you are satisfied with your theoretical geometry, then you can have a 3D printed version of that impeller, and then you can go for the real experiments. Okay, so this is how ANSYS CFD can reduce the loss of money. Like before even having the actual spending rupees on having a real impeller, you can have a design, and you can simulate and see how it is effective. Okay, so that's why many industries are now also following the same. Like they are investing on ANSYS simulation so that they can have a pre-idea of what they can achieve. Okay, so starting with the geometry design, let's say this is an 1,000 liter reactor. So with this, I will not, obviously in this short frame of time, it is not possible to show you every like how to draw the geometry, but I will just give you an overview. What are the major steps that you should do when you have this when you are doing the geometry design. So first is definitely since it's the fluid design, so you should always consider the region of the fluid to work on. So basically, as you can see, that we do not need the headspace when you are doing this reactor design. We are not supposed, we are not including the headspace in it, because the air, how it is agitated inside the reactor, it is not the area of our interest. We have our area of interest is more towards the liquid region, right? Next is the solid regions, like the baffles blades, the impeller blades, the impeller shaft. Those are solid regions, right? Those where how the energy goes inside that, how it is rotating. Those are not our area of interest. Our simple area of interest is the region where the fluid exists. So you can just have those are void, like as I showed here. Those can be removed, as can only the walls need to be there, right? So next is your sparger. The sparger has to be designed properly. And second, next is having a MRF zone. What is a MRF zone? Is a moving reference frame. We cannot rotate the in when you are doing an ANSYS CFD, you do not rotate the impeller blades. We rotate a zone around the impeller blades, which consists the impeller blades. Okay, so and the impeller blades are actually stagnant. So the momentum transfer happens near to the wall of the impeller blades. So okay, so around here, so obviously this region is rotating. So and here your momentum and energy transfer will take place. So basically that's why it is called moving reference frame zone. Okay, and the most important step in geometry design is having no overlapping regions. Okay. Next, this is a 1.2 liter glass reactor from our lab itself. So this is how we design it. Uh, we take the measurements of all the parameters, and since the working volume is only 600 ml for this 1.2 liter reactor, we only consider this much region for our geometry. We do not need the entire headspace. Next is having the MRF zone, rotating frame of motion. So these has to be, there is some imaginary bodies that is drawn around the uh, inside the fluid zone. Okay. So next comes the meshing. Coming to the meshing part, you can have this type of meshing, like the rectangle, the triangular mesh. So these are the meshes basically you use for the 2D geometry. When it comes to a three-dimensional geometry, you have the tetragonal, hexagonal, prism, pyramids, and polyhedral geometries. Okay, so the most critical aspect while having this meshing this geometry is the is the is understanding how it works. Like, so let's consider this rectangle geometry. You have obviously four nodes. These four dots are called as nodes for the geometry for the maze. And you must have heard something in ANSYS CFD is called pressure velocity coupling. The reason why that term is used is you see the velocity the calculating the velocity, you need a direction, the direction vector, because velocity is a vector. So you need 2 points to calculate the vector. So velocity is always calculated along the edge of this rectangle. Similarly, for tetrahedron, your velocity will be calculated along each edges of this. And considering about the pressure will always act on the surface, like force per unit area, right? So you need the pressure will be calculated over here. The velocity will be calculated along the edge, and and your temperature will be calculated on the points, like the because the temperature is a scalar unit, right? So the to understand, this is how you should understand why you use the pressure velocity coupling model. Next is what are the major parameters you should be considering while meshing. So your skewness should always be less than 0.9. So when I say skewness, basically this is how your skewness increases. So if you have a rectangle, a good rectangle, like having 90-degree angle at each corners, you say you can have, this is your skewness will be less than 0.01. As it starts getting inclined, the angle is reducing, your skewness increases. Okay, so when you are meshing, sometimes this kind of mesh also gets created, which have a high skewness, like beyond zero point 0.9. Such such a mesh is very difficult to process for the model for the ANSYS CFD. That's why such a mesh should already be rejected. So you should always stay below zero point 0.9. Okay. And next thing is aspect ratio. These are the two major points that we should consider. The skewness should be less than zero point 0.9 and aspect ratio should be less than 30. What is aspect ratio? Aspect ratio is basically if you have a rectangular mesh and how your mesh is growing for the mesh growth is happening on the surface. Like if you have this small rectangle and having unit 1, and the next area is like 4 times of the original area, and the next size is 4 times of the original, like in this way it is going. And so instead of going like this, you will go directly jump from the smallest to the largest. So this will definitely have more like more errors more errors in your missing and in your results. So when you go for grid independent study, this is how you do. Like I have done this for a 10-liter reactor or 10-liter bioreactor, and as the reactor as I increase the number of elements like 10 lakh to 15 lakhs, 20 lakhs, 25 lakhs, you see the my KLA value starts to like linearize, like this gets saturated. It is not varying any further. Initially, when it is below 10 lakhs, my KLA value is beyond, like have an error beyond like 20%. Usually we go for error less than 10%. When you have less than 10% error, you can take that mesh size for your future applications. Okay, so when you go for case setup, a simple case setup is like having a Euler model. With water will be a continuous phase, air as a dispersed phase, and viscous model is like KXL model with standard wall function, realizable method you use. Now this is how you can implement your reactor, your ANSYS to calculate the KLA, and to see how the oxygen concentration is actually increasing with your mass transfer rate and KLA variation. So you can do multiple simulations to achieve these kind of results and see whether your KLA matches your O2 concentration level experimentally. So when you have the error less than 10%, you can say your model is valid. This is an experiment we have done to have a correlation for mixing time. So mixing time plays a major role in many reactors, like how quickly it mixes, right? So if you see how we do is we use the simple titration method that we use in 10 12, right? In titration method you have a solution, acidic solution, put some phenolphthalein indicator and add some base into it until it balances, and the time it takes to mix, it's called will be considered as a mixing time. So you can simply record this video in a slow motion, and you can see which correlation best fits your model, right? You can see here we are matching almost our correlation values, and the experimental values are matching very well. We did repeatedly, did this, and finally we concluded this model is well suitable for our reactor for mixing time. Okay. Next is like for validating thermodynamics. So to validate thermodynamics, what we do is, since many reactors doesn't comes with an inlet temperature and outlet temperature, right? We always have this thermocouple that measures the water temperature inside it. It doesn't have the cooling water temperature and outlet temperature of the cooling surface, and the mass flow rate is also unknown. So what we do is we integrated some instruments that is found online, like in Amazon. We purchased this Arduino board, breadboard, have some thermocouples, and have a uh, have this here. Here's the mass water flow rate measurement that we have done, and all this we did it ourselves. We integrated it to the reactor, and we measured the values. Now see how well it recorded the data and how well we are able to achieve with the data. So as you can see, the red line, the dotted line over here is the experimental value, and to heat the actual process, we use some polynomials, like 4 polynomials. The entire zone can be divided into two heating and cooling cycles. And here it is the water temperature, how the water temperature is changing inside the reactor. So how we are this is like less than 10% error is achieved. Hmm. And next is you can see the effect of shear. The When you are growing some cells inside a bioreactor or in the fermenter, the major part that is affected is shear resistance, right? The cells have some shear resistance. If you put higher shear, the cells may burst. That is there is a very difficult thing in mammalian cell as compared to in microbial cells. So usually in microbial cells, it is not recommended to go beyond 300 rpm. So this is the reason why, because the shear resistance for the mammalian cells is somewhere around 1700 to 2000 uh, strain rate. Okay, so in this contour plot, you can see how the shear rate is increasing near the impeller blades. That's why you do not use the Ruston turbines inside the mammalian reactor. So in this way, you can design your own reactor. You can design your own impellers for various purposes. Suppose you can able to design a better impeller blade for a mammalian reactor, which can go more than 500 or 600 rpm with less shear affected effect. That will be really good, which can increase the mass transfer coefficient, right? So next is the advanced level, is how this is the basic Monod equations, the differential equations when you grow some cells inside a inside a bioreactor. Excuse me, inside a bioreactor. These are the basic equations that we follow with the Monod Michaelis-Menten equation, Monod equation. That we all know about these equations, and we have derived it in multiple steps. And when you integrate this with the bioreactor using user-defined functions, then you will have the cells growing inside the reactor as a digital twin of a bioreactor, right? So how you can approach is like change the substrate concentration, the aeration rate, and have a lot of contours, and then find an optimized region to operate, and then you can have a model for this, right? So I I think thank you for this, and I think I have given you enough for this. I think you have an idea for how you can do this. Okay, so those who are interested in learning how to do the geometry and simulation, they can follow me in my YouTube channel. And I think if you have any questions, let me know. So here in this, I have already sent in the chat on my YouTube ID. So I think those who are interested in doing ANSYS CFD and they are stuck at some point, they can contact me. I think this the wonderful story comes with like I'm not very regular. I do not upload it very regularly, to be honest, here because I also have to do my own PhD work. So what happened is someone from internet searched me from China, and they reached out to me to solve their problem. That is a wonderful experience for me. When they reach out to me and I am able to, they are very thankful for to me. Like I'm able to deliver what they have been stuck with. So if you have designing, or if you have some issues with ANSYS CFD, or if you are planning to go with this can be a good step where you can learn something regarding ANSYS CFD, and you can have your questions.
So, like one question I have in mind. So,
Mhm.
like we work with bioreactors, and also like bioreactors, we can think of them as a like controlled way of doing fermentation in a sense. Like
Mhm.
fermentation would be pretty vague term, but like so in cases where there is a contamination, so you
Mhm.
must have dealt with it. So, like, is there a way to identify it through the software, or like how do we deal with it? If you can give a brief information overview.
It's see for designing any model, like suppose you are saying about contamination, right? The basically the contamination comes from any leakage or any void space that you have, like where the atmosphere that atmospheric cells or the atmospheric bacteria gets into your reactor, right? In that way, we have to design it that way. Like we can find a way whether it is contaminated or not. Like we can give you can give some possibilities over here. Hmm. So you obviously, yes, you can do it, but that is like you have to draw, you have to design, you have to see where the leakage is first of all, whether there is the contamination possibility, where the holes are, and giving a chance that okay, suppose there is a rubber ceiling, you are thinking that okay, from this rubber ceiling there might be some air coming inside. So you have to give some inlet conditions, the minor inlet conditions for those where the cells atmosphere can contaminate your reactor, right? That can be modeled. What I'm saying. Say.
Yeah, that's uh, like there needs to be particular conditions for it. I think, yeah.
Like we have to give particular boundary condition for it. Like the way you give the air inlet boundary conditions, you have to give that boundary condition over there.
Yeah, thank you very much, Nirmal. And like, are there any questions from participants? So if there are questions, this is a golden opportunity for you guys to, uh, get insights on anything. Like, uh, be it anything. Like, if you are not able to, uh, like, think of something related to bioreactors, you can ask in general. Like, I have introduced, yeah, like, Nirmal here to him. So, like, he's a pretty well established researcher. So if you guys want to, like, know anything about him, or you want to ask something in general, so then also you can uh, do so.
Okay, can I ask like what are you currently working on? I mean, if that's okay to answer.
Yes, Susri, right? Okay. Susri, I'm currently working in the bioreactor optimization itself. Like I am working on an industrial project where I have recently done some simulation for a 300-liter bioreactor for Premas in which is a established company in I think in Gurgaon. And basically what we do is we model their geometry, we take the geometry data from them, and what we do is we study their reactor, their conditions, aeration. We keep the aeration inlet and agitation conditions to the bioreactor, and see how the mass transfer coefficients is actually varying, and where it is not able to, which area or where it is the mass transfer coefficients are less, so which needs to be modified, or that kind of stuff. Like so, optimize basically it is optimization or design.
So, what factors do you really consider for this optimization of the bioreactor? If you like to like say something about it.
Bioreactor depends upon various things. As I said, currently, like mostly what people have previously done is considering the only the agitation and aeration rate. There is very less literature you can find regarding the effect of temperature, regarding the effect of head pressure. Obviously, as a engineer point of view, you know that how the temperature affect the saturation of O2 in any media, like your content, right? So that kind of studies, that parameters that you have to study, and the deeper you think about it, the more the answer you will get. Like it is depends upon how you actually how persistent you are towards the problem, the
Okay,
parameters.
so mostly the agitation and the aeration like factors are
Head
considered.
pressure, head pressure, temperature, right? The geometry, how it is affecting the impeller blades. Those are the things.
And I had heard about this one-time use bioreactors. So, and I had read somewhere that they
Hmm.
might be more beneficial for the industry rather than what we are currently, like the one that we're
Hmm.
using, reusable ones. So, like,
Hmm.
what is your take on that?
We have done from our. I haven't done personally, but from our lab we have done the one time. We have used the one time bioreactor, and actually currently from the lab scale prospect, it is not feasible. Actually, maybe you are saying, yeah, there is some literature for publicity. People are doing this, but for lab scale purpose, it is very hectic to maintain a one time use bioreactor. Uh, because there is obviously one time there is obviously contamination issues are the major thing in the one time use bioreactors, but we have done the simulations for it, we have done experiments for it, we have plans to
Mhm.
do in future. Okay.
So, for industrial scales, do you think it's better or like the other, like whatever is currently going on, that is the better one?
I think depends upon your scale, at what scale you are operating in the for industry
For
scales is, hmm,
it
for
might be.
1000. Yes.
Sorry, go on.
Like go ask, you are saying something.
So I was asking, so for large scales, it might be better. Like we
Yeah,
cannot.
no, for large scale industry, the current methods, the current reactors is actually better, because the one-time use bioreactors contains is basically polythene based UV based polythenes, so that cannot hold the pressure that much. So you have to design that containers that effectively. Mm. In my point, I'm not sure. I haven't done it industrially, but I am thinking this. Okay. So I haven't seen any industry using a 1,000 liter bioreactor for one-time use.
Okay, thank you
So
for
you are
this.
working in which direction? May I know if you can?
I'm not working in research, but I have completed my MTech in biotechnology. Currently, I'm kind of working in business-related profiles for biotech
Okay.
industry. So,
Okay.
but I
Okay.
join PhD, like that's
Hmm.
on the list, but not sure. So
Hmm.
I have
Okay.
research as
So
well.
we have used, actually, to be honest, we have used by one-time use bioreactors, but we have faced as many issues. So currently we have our reactor is still sitting inside in our lab.
Mm-hmm.
But so that's what my take
Yes,
is.
that's why I was surprised. So I had read it somewhere. I was like, how could it be more feasible? And that
Yeah.
doesn't make any sense, right? So I thought I'll ask.
Huh. Yeah. Even you can find some literatures if you look for A. Stratford in the Google Scholar. You can find the one-time use bioreactor simulation done by my senior Somesh Misra. You can find his paper.
Sure, I'll look for it. Thanks. Thank you for taking this question.
Thank you. So, is there any other questions?
So Tanvi is asking in chat, what is the need for one-time bioreactors? Is there any specific need for one-time bioreactors, or are they just uh,
Yeah, many times people use one-time reactors for mostly for mammalian cell. We use that for mammalian cell only, because somehow that is like I cannot what I can say how can I say, like for mammalian cell only we use, but in the industrial level you cannot go for that much bigger scale. Hmm.
hmm. So hope that answers your question, Tanvi. And is there any question? Any more question? You can just unmute yourselves if you are unable to write it in the chat box. Everyone has access to the mic.
I think Utkarsh is typing something. Uh, yes, Utkarsh, like you can use machine learning algorithm. I think you might have heard or not. Like currently, ANSYS is also putting launching his uh, chat ANSYS chatbot, and now ANSYS is also using machine learning algorithm for this purpose. Like you can have your reactor design, one multiple reactor design, and have your simulations. And in future, how you can what you can do is, when you have a reactor, it will automatically take the parameters of the reactor, like the blade size, the size of the volume. On that basis, it will predict the results. So basically, instead of doing the simulation by hand, by that time, like for spending like hours or days on the simulation, you can have predicted values through machine learning within minutes. So that is the outcome of application of machine learning in CFD. I hope that answers the question.
I think there are no more questions, and thanks
I think
Nirmal for.
Tanvi is writing something. I think last question we can take from Tanvi. She's writing something.
Okay.
Then you can directly ask in the mic. Okay, fine.
Yeah.
I think there's no more questions. Okay.
So since I think there are no more questions, and thank you Nirmal for patiently taking all these questions and coming on such a short notice for this session. And thanks for delivering such an insightful session. And I hope students have also learned a lot from you. And I hope you have also enjoyed delivering a session
Yeah, I
on
always
this topic.
enjoy teaching. I used to teach before, which I forgot to mention to you. So I enjoy teaching before. So I put my mail ID over here. If you anyone interested in have any questions in CFD modeling, so they can reach out to me in my mail also. I will be happy to answer you. Okay. So I have put my
That's
mail
really
ID.
great of you. Yeah.
Thank you. Never
Hmm.
mind. Okay. Thank you. Okay.
Thank
Should
you.
I leave? Okay.
Yeah, thanks. We should maybe we can conclude the session.